In this video, I'm going to show how to solve for the Nash equilibrium in one of the most popular games in game theory, the prisoner's dilemma. The prisoner's dilemma refers to an imaginary situation in which two individuals are arrested and they're accused of having cooperated together to commit a crime. The two prisoners are held separately in jail cells and they're not allowed to talk to one another. And attempts are made by the cops to induce each one to implicate the other in the crime. And the cops propose the following situation to the prisoners. They tell the prisoners that if both stay silent and neither one refuses to rat the other one out, then they're only going to go to jail for 1 year because there's not enough evidence to convict them of a more serious charge. However, if both prisoners defect and they rat each other out, then they've confessed to the more serious crime, and so each prisoner is going to go to jail for 3 years. Now, if one of the prisoners stays silent while the other defects, then the prisoner who stays silent goes to jail for 5 years, while the one who defects and rats him out gets to walk away. He doesn't go to jail for any time. And each prisoner has the identical options. Either one can defect and rat him out or stay silent. But they only get to make the choice once. There's one shot to make a decision of whether or not you want to defect or stay silent. Now, with this information, we can represent the following game in a matrix. We call this matrix the normal form of a game. And to represent a matrix in a game, I need 3 pieces of information. I need to know the players involved, and I've indicated those players as prisoner 1 and prisoner 2. Second, I need to know the strategies that each prisoner can take, and those strategies are they can either defect or stay silent, and both prisoners have the same strategies. This doesn't always have to be the case in a game. They can have more than 2 strategies. They can have different strategies. But in the prisoner's dilemma, they have the exact same strategies. And the third thing, the third piece of information that I need to know is the payoffs to the players. So if prisoner 1 defects and prisoner 2 defects, I look here inside the cells of the matrix to see the payoffs to each prisoner. So if prisoner 1 defects and prisoner 2 defects, the first coordinate in the pair is the payoff to prisoner 1. So prisoner 1 goes to jail for 3 years. And we can see that prisoner 2 also goes to jail for 3 years when both players defect. Now here, if I look at this cell and I see that prisoner 1 defects and prisoner 2 stays silent, then because prisoner 1 defected, he gets to walk away. So he goes to jail for 0 time. And then prisoner 2, however, goes to jail for 5 years. And I can see here at the bottom of the matrix that if prisoner 1 stays silent and prisoner 2 defects, then prisoner 1 in fact goes to jail for 5 years and prisoner 2 gets to walk away. Now in the last cell of the matrix, I can see that if both players or both prisoners are silent, then each one goes to jail for only 1 year. Now to solve for a Nash equilibrium, I need to know the definition of a Nash equilibrium. A Nash equilibrium tells you that no player has any incentive to change the strategy that they currently have taken. So in other words, it's a mutual best response. Given that prisoner 2 pursues a certain strategy, and I choose a strategy, if the if the set of strategies is a Nash equilibrium, then neither party has anything to gain by changing their strategy. And we'll see how this plays out. So if prisoner 1 defects, I need to choose my strategy if I'm prisoner 2. So to choose my strategy, I compare the payoffs for defecting to the payoff for staying silent. So prisoner 1 defects, I can see that if I'm prisoner 2, I'm better off to defect because -3 is better than -5. I'd rather go to jail for 3 years than go to jail for 5 years. So I indicate that by putting a check mark over the second coordinate in that pair. Now if prisoner 1 stays silent and I need to choose my best strategy as prisoner 2, I'm comparing 0 to -1. And again, if prisoner 1 stays silent, my best strategy is actually to defect because 0 is greater than -1. And you can see here that for prisoner 2, defecting is actually a dominant strategy. Regardless of what player 1 does, it always makes sense for me to defect if I'm prisoner 2. And if prisoner 2's dominant strategy is defecting, we can say that staying silent is a dominated strategy. Now let's go through and see what prisoner 1 should do if prisoner 2 takes a particular strategy. So if prisoner 2 defects, I need to decide what to do if I'm prisoner 1. Do I in fact defect or stay silent? So again, I'm comparing the payoffs of -3 and -5, these two values here, and I'm better off to defect. If I'm prisoner 1, -3, I'd rather go to jail for 3 years than to go to jail for 5 years. So in fact, I go ahead and defect, and I indicate that by putting a check mark over the -3. Now if prisoner 2 stays silent, and I have to decide whether or not I defect or stay silent as prisoner 1, again, if I'm prisoner 1, I'm going to defect, because 0 is better than going to jail for 1 year. So it makes sense for me to in fact defect in this case. And now again, look at the strategy for player 1 or prisoner 1. Regardless of what prisoner 2 does, it always makes sense for prisoner 1 to defect. So again, I say that prisoner 1 has a dominant strategy of defecting and a dominated strategy of staying silent. Now a Nash equilibrium is indicated here by prisoner 1 defecting and prisoner 2 also defecting. You can see that I've got the check marks over both payoffs. In other words, this is a mutual best response. Neither party has an incentive to deviate from that strategy. So if prisoner 2 defects and I'm prisoner 1, I'm not going to stay silent, right? Because -5 is worse than -3. And if I'm prisoner 1, if prisoner 1 defects and I'm prisoner 2, then I have no incentive to change my strategy and stay silent, because -3 is better than -5. So whenever you have a mutual best response, you have check marks over both of those payoffs, then you know that you have a Nash equilibrium. Now we're not guaranteed to have only one Nash equilibrium. In fact, we can have multiple in some games. But in this case of a prisoner's dilemma, the Nash equilibrium is that both prisoners are going to rat each other out or defect. Now what makes the prisoner's dilemma interesting is that because both prisoners have pursued a rational response, they do what's in their best interest, they're both worse off when they both pursued their best interest. See that when they both defect, they each go to jail for 3 years, for a total of 6 years in jail. But what happens if they both stay silent? See, when they both stay silent, each one only goes to jail for 1 year. And so the total amount of time spent in jail is 2 years. So the prisoner's dilemma illustrates how when individuals pursue their own best interests, sometimes society as a whole can be worse off than if each one was able to cooperate.